Hi, everyone, and thank you for joining us today. We're excited to share an update about our research supercluster, recently completed this past fall. We had started effort on it last year, in 2021 actually, and completed the first phase in 2022, and finalized everything at the end of October, November timeframe. But for now, I'm going to set the groundwork for you as to why we built a research supercluster in the first place. Meta has been using AI in a lot of different ways for many years. Whether you're talking about flagging harmful or toxic or biased content in our application space, or if you're talking about translating a language instantaneously, if you've been in the Facebook app and you've clicked on the translate button, you know that that's machine learning that's doing machine translation for you. This is a significant area of investment. And later on in the presentation, I'll talk about one of the projects, No Language Left Behind, that's in this space. And then also the advent of AR and VR, whether you're using an Oculus today or you're thinking about what it will be like in the future, the use of AI is essential to these platforms. Whether you're talking about the placement of you within your room or how your hands are moving, these are all things that are driven by AI. And as these platforms grow in importance and scope, AI is going to play an even more important role. And being able to do this across billions of users in many different countries on all of our platforms, this is just a very ambitious scope of work, and it requires research to underpin it. In addition to that, we have to be aware of our use of data to train our research models, being able to track that data and make sure that it's logged and it's stored in an appropriate way and that it's encrypted. All of these things are important. But also, it's important to make sure that the access to our research platform is a controlled environment and that unauthorized access is a default feature. And so my peer Kalyan will be talking a little bit about some of the technology that we've put into the RSC that helped in this way. In terms of how we approach research and how we continue to improve our AI functions at Meta, our research community is constantly looking at ways of increasing the amount of data or the quality of the data or the source of the data to improve our training and diverge different modalities of data, whether you're talking about training a language model with just text, or perhaps you want to train your language model with text and images to enhance the richness of the output. That's one way. In addition, you may want to increase the complexity of the model, whether you're talking about adding parameters or you're talking about pre or post processing that's being added into like a model workflow. Those are areas of focus too. But to do all of these things, you have to learn from what you did and make improvements and tune and iterate. And that requires rapid iteration and rapid innovation, which involves time. And so that has a direct correlation to how much resource you're able to run on for your investigation or for your final output. An example of how this has become important to us is in the large language space. If you look at the chart here, this is the number of parameters being used for large language models in the last 5 years. With the advent of the transformer technology, that allowed for a lot more parallelization and scale, which meant that you could add many, many more parameters. And you can see the growth of parameter counts has gone exponentially since 2018. We're now approaching 1 trillion. And the more parameters you add, the more data that you add, the longer it's going to take to process if you don't have sufficient scale. And we knew this because we've been using AI for a good while now, and we decided to make an investment in a large cluster. You can't build these overnight. You have to plan. There have been some challenges in the past few years, as I'm sure we're all aware, that COVID has impacted supply chains, and we had to factor all of these things in. So this was a multi-year effort, very forward-looking, and we're very happy that we've come out on the other side with a fully functional cluster. And on that note, I'd like to hand off to my peer, Kalyan, who's going to talk about the details of the cluster and the lessons that we learned.
Thank you, Scott, for the introduction. Hello, everyone. My name is Kalyan. I'm a software engineer in AI research infrastructure team at Meta. I happen to work on ML training, production ML training, and large-scale distributed systems at Meta and VMware before joining the current team. Let's jump into the question, why build a custom supercluster instead of using the existing data center technology that Meta has deployed all over the globe? It really comes down to understanding and realizing the unique demands large-scale AI training places on the infrastructure. This translates into our need to control the physical parameters. What are the physical parameters? I'll highlight three of them. Number one is cooling technology. Airflow-based cooling was not meeting the mark for large-scale AI training for us. So we had to go with liquid cooling, which was a departure from Meta production data centers. Given the rack density, given the number of GPUs we wanted to pack in the data center building, this meant that the power requirements significantly deviated again from the production setup. But there is one more important aspect, that is the specialized flat backend network. This is low latency, high bandwidth network with constraints on the cable length. Again, constraining the physical parameters of how far you can spread these GPUs. When you put these three together, we had to make a choice that we needed a custom cluster. So let's look at what is research supercluster at a high level. I want to quote one number, that is aggregate compute power from RSC is up to 5 exaflops of compute power, right? That is 1 billion operations per second times 5. So this is an enormous scale. How do you get this scale? What does it take to support the scale? Let's drill into the building blocks of the cluster in the next few minutes. The first and foremost is the fast and flat network. What's fast about it? Each server has 8 Infiniband links. This is 2x more than the prior generation. Each link is 200 gigabits per second, again 2x faster. And most importantly, there is no oversubscription in the network. When you zoom out from the server level to the entire fabric, we believe this is one of the largest known flat IB fabrics in the world. To quote some numbers, the fabric has 48,000 links, more than approximately 2,000 switches, including edge and spine. This is a lot of entities, right? I believe 20K nodes is what is reported by Infiniband network there. We talked about the speed and the scale, but there is a very important qualitative aspect to the network, the way we designed. We repeatedly emphasize the flat nature of the network. What are the benefits of flat network? It presents, the scheduler sees a homogeneous set of resources. Again, translating to researchers' perspective, they are free from having to worry about what performance they get if they land on XYZ nodes versus ABC nodes. This is like degrees of freedom that our researchers really appreciate. Workloads are free from topology awareness. As a result, there is no resource fragmentation in the cluster, and we get to train more jobs and at a larger scale. Let's put these design aspects together and see what bandwidth do we get from this network. As an example, if we run a 4096, that is 4K GPU nickel all-reduced benchmark, we get 157 Gbps in-place bus bandwidth. And that's already pretty good, right? This is without optimization. As recently as a couple of weeks ago, we managed to optimize the network further with Sharp, and we are seeing close to 211 Gbps nickel all-reduced bandwidth. That is a tremendous performance that we are able to extract out of the network. Let's move on to the next building block, that is the powerful compute. Even if you have the fast and flat network, if the compute nodes are not good, you're not going to get the 5x of flops that we promised, right? What do we have as the compute nodes? We have 2,000 NVIDIA DGX A100 systems, which was the latest generation available at the time of the cluster build-out. Each server has 8 A100 GPUs. Each GPU has 80 GB memory, totaling up to 640 GB. And we also have a front-end network, Ethernet network at 200 Gbps throughput. The goal was to fit as many of these GPUs as possible, which ties back to the need for custom cluster. Now that we have talked about the compute, let's move on to the next building block of the cluster, that is storage and data. AI training at the scale is nothing if we cannot supply the data fast enough to the GPUs, right? With that in mind, let's see why we had to build a custom storage engine. Early on, we realized that the special properties of training data and the demands it places on the storage systems meant that we had to create a special purpose storage engine called AirStore, the AI Research Storage Service. AirStore improves the data loading performance and scalability. What happens in the background is that we have dozens of flash arrays and we have hundreds of cache nodes. We pre-process the training data and distribute the bundles across the flash arrays. The cache nodes fetch the data and keep it ready for the GPUs to pull the data when they need a particular sample. AirStore is a complex storage service that we built and which requires a dedicated presentation of its own. I'm only highlighting the important aspects. Yeah, when you orchestrate this, what this means is that you are able to achieve 10 to 100x reduction of disk seeks and RPCs. This is very important to keeping the hungry training nodes busy with data. Let's look at the other aspect of storage, that is NFS. We have 10 petabytes of flash storage mounted and visible to every device in the cluster. This storage is used for intermediate checkpointing and code, logs, and other transient data that jobs produce. Why is this a very important aspect of the cluster in a job's lifecycle is that jobs can start training, interrupt themselves, resume on a different node from a previously taken checkpoint. This makes it easy to handle both failures of job as well as stop, suspend, and resume of job at a different point in time because you have the checkpoint available across the cluster. I want to take the opportunity to re-emphasize the commitment to privacy and security in the cluster because we encrypt data at rest and in line. All samples are only decrypted when the GPU wants to consume them, and then the data overall has a TTL, beyond which the data is deleted and wiped away from the cluster. Now we have the compute, the network, and the storage systems. This makes for a pretty powerful compute infrastructure. How do you offer it to our researchers? Researchers need to be able to consume the resources in an easy manner. For that, we built a purpose-built control plane, and we use an open source scheduler called Slurm. This is a HPC scheduler that makes job management fairly easy for researchers as well as the cluster administrators. Let's walk through a flow. Users simply submit a batch job, and that enters the job queue. Based on the priority, based on the resources available and the resources required, Slurm picks up the job and places it on a set of nodes. Remember, our cluster is homogeneous. That means that Slurm is able to pick any subset of nodes and place the job. And as jobs finish, slots become available, new jobs can land on the nodes. Now that I have described the building blocks and highlights of various storage systems that we built, let's move on to some of the lessons we learned while building and operating the cluster. I'll start with one significant aspect. This entire cluster of 16,000 GPUs was not built and delivered as a one-shot exercise. In fact, we did this in 2 phases, during COVID and remotely. But more importantly, the phased build-out was done in a non-disruptive manner, where 40% of the capacity was made available a year and a half ago, and we continued to build and expand the cluster. This required some good planning upfront so that we have the ability to extend the cluster without disrupting workloads. A few more lessons that we learned and we incorporated into the second phase of the cluster. Number one is failure rates. The hardware failure rates were higher than we anticipated, and this required us to build better detection, remediation mechanisms to ensure a stable and reliable cluster and offer a seamless experience to our researchers. Next up, as I mentioned before, Our fabric is one of the largest flat IB fabrics in the world, especially at the scale. This forced us to do pioneering and groundbreaking work to find the bottlenecks, find the performance bottlenecks, tune and sustain the performance of the cluster over a long period of time. And these lessons were incorporated into how we brought up the rest of the cluster in phase 2. The third aspect is when you have a high performance compute infrastructure and a lot of projects want to run their jobs on this cluster, how do you offer these resources in a manner that is controllable and can prioritize and can implement the business priorities? We work closely with Slurm's scheduling and priority primitives to incorporate the resource quotas and priorities so that the right jobs consume resources at the right time. I want to cover a few more lessons that we picked up during the operational phase of the cluster across both phase 1 and phase 2. As mentioned before, GPUs fail in multiple ways. They both hard and soft failures. This requires different detection and remediation strategy. For soft failures, you can get away with tooling that can fix the state of the GPU. But sometimes you may have to go towards a parts replacement and have a longer remediation cycle. The second part is network stabilization, especially at the scale when you're talking about 48,000 links, is a pretty hard problem. Every component becomes a suspect, starting from the NIC attached to the server, the cables linking nodes to switches, the edge and spine switches themselves, and the internal switch links, ISLs. When you have these thousands of fiber cables, a lot of physical factors play a role here, including the bend radius, the temperature, and any other degradation can affect both performance and functionality. So network stabilization is a hard problem, both during the build-out phase as well as ensuring a stable cluster. One other key takeaway that I want to emphasize is that in such a large and high-performance setup, when your workloads misbehave or fail, the symptoms are for several layers removed from the root cause. This means that you have to have very good observability and debuggability infrastructure investments to be made, because you can have bad nodes, memory, faulty cables. All of them can result in a completely opaque symptom experienced by the job. Now that I've talked about the why and what of the cluster, I want to hand it back to Scott, who will go over case studies of models trained on RSC.
Thanks, Kalyan. Now I'd like to talk to you about a couple of the projects, and then we'll wrap up. So I'd like to start with the Llama project we just recently released. The research team was trying to address a few different concerns or tackle a few different problems. One question was, let's say you're a researcher and you want to understand how large language models work, and you're in the general community or you're at a college or whatever, and you can't really run something like a GPT because you don't have the scale of facility, the scale of infrastructure to do that. So one of the drivers was to release a set of foundational models with much smaller parameter counts that would be available to the research community to help them better understand LLMs and to potentially innovate beyond the foundational model themselves. That was one of the agenda items. The other goal was, could a model trained for a longer period of time with perhaps more data, but smaller parameter counts, yield similar results to some of the state-of-the-art language models in terms of quality of responses and accuracy? And I would encourage you to take a look at the research paper. That will give you all of the findings. They had some interesting results. One of the keys is that they were able to use the RSC to do rapid training. They were able to speed up their training significantly from prior efforts in other environments that helped them get to their deadline much faster. In addition, the stability of the cluster during their training epochs allowed them to run without interruption for multiple weeks at a time, which allowed them to get to their results quicker as well. So this is an excellent example of a project that was able to leverage the scale. The largest model, the 65 billion parameter model, was trained on 2,048 GPUs, and they were able to dramatically decrease the amount of time it took to complete that. In addition, I mentioned this earlier in the presentation, we had the No Language Left Behind project. NLLB, I had mentioned this a little earlier in the presentation, is a project that was designed to look at, could we do machine translation for languages without a lot of data on the internet? And the team has done a wonderful job. They released an excellent research paper I encourage you to look at. The research supercluster enabled this team to dramatically speed up their training times from where they were. On the previous generation cluster, they were around a month per epoch. Running on RSC, they were able to drop their training times down to around a week, which allowed them to speed up and improve the output and get to their research results in time. So in conclusion, the research supercluster offers two key ways to scale. One, the ability to scale the state of the art. So can we take a single model and go big? Can we go with thousands of GPUs for a single model? That is a key aspect of the RSC. But the second way is the ability to scale out and have many projects running. Because of the nature of the network and the architecture, the ability to run multiple simultaneous projects without interruption or without impinging on each other is available to our research community. This means that we'll be able to take on projects, offboard projects quickly, and scale our research efforts here at Meta. In terms of infrastructure innovation, we will continue to look at how we build RSC, how we operationalize it, better engineering practices, how can we improve it, what could we learn from our efforts that we could apply to any future endeavors, and also to share our learnings and to share our thoughts and processes with our peers in production as we drive towards the future. And with that, I thank you all for attending our presentation.